All right, let's get right into it. Today, we're looking at a pretty wild idea, one that could completely change a fundamental rule of physics. And you know where the test for it is? Right at the edge of the craziest objects in the entire universe, black holes.
So think about this for a second. What if infinity isn't real? I mean, what if it's just a neat trick we use in math, but not something that actually exists in the physical world? For more than 100 years, physics has been kind of haunted by these things called singularities, these points of infinite density, infinite energy, the center of a black hole, or even a tiny particle like an electron. But what if nature has a built-in off switch that just says, nope, you can't go to infinity?
Well, that is the big idea behind a really cool theory called Einstein-Born-Infeld, or EBI for short. The easiest way to think about it is like a cosmic speed limit, but not for how fast you can move. It's a speed limit for energy itself. It suggests that just like you can't go faster than the speed of light, you can't just keep cranking up an electric field forever. At some point, the vacuum of space itself pushes back, stopping the field from ever hitting infinity. Okay, so that's the big question, right? How in the world do you even begin to test something like this? I mean, the effects of EBI theory are totally invisible in our day-to-day lives. To actually see them, you'd have to find a place where the gravity and the electromagnetic fields are so unbelievably intense that they're literally pushing the fabric of space-time to its absolute limit. And that, of course, brings us to our cosmic laboratory. The space right around a spinning electrically charged black hole is pretty much the only place we know of where these effects might be strong enough for us to see them. It's the perfect stage for a showdown between Einstein's general relativity and this new kind of physics. So, let's say this energy speed limit is real. What would we actually see? How would it change that iconic image of a black hole that we all have in our heads? Well, it turns out researchers have made some very specific, very testable predictions. Let's start with the first clue. The first big hint would be in the black hole's silhouette, what astronomers call its shadow. You know, that dark circle we see against all the glowing gas swirling around it? The exact size and shape of that shadow tells us a ton about the spacetime right at the edge of the black hole. And this image shows that first prediction beautifully. That red circle, that's the shadow of a black hole, if EBI theory is right. The blue dashed line is what standard general relativity predicts. See the difference? Because EBI theory messes with spacetime right near the event horizon, it changes how light bends around it, and the end result is the shadow actually shrinks. And this isn't just some vague idea. They actually put a number on it. For a black hole with a really strong charge and the right EBI field strength, the shadow should be about 5% smaller in diameter. Now, I know what you're thinking. 5% doesn't sound like a lot. But for the massive, planet-sized network of radio telescopes that makes up the Event Horizon Telescope, yeah, the same one that took those first-ever black hole pictures, a 5% difference is right on the edge of what they might be able to detect. This is what takes the theory from just an idea on a blackboard into real, testable science. But a smaller shadow is just one piece of the puzzle. The second prediction is, honestly, even cooler. It's a potential smoking gun for this new physics. And it's all about how the vacuum of space can literally twist light. It's a crazy phenomenon called vacuum Birefringence. Basically, in the insane environment near an EGI black hole, the vacuum isn't empty anymore. It starts acting like a crystal. The researchers described it as a giant twisted polarized lens. So when light from behind the black hole passes through it, its polarization, the direction its waves are wiggling, gets rotated. And here's where it gets really good, because there's a fundamental disagreement here. Both EBI theory and our standard model of quantum physics, that's quantum electrodynamics or QED, they both predict this twisting effect. But, and this is a big but, they predict it will behave in totally different ways as you get closer and closer to that black hole. This graph shows you everything. That blue dashed line is the prediction from QED. The closer you get, the more the light twists, and the effect just shoots off towards infinity. But look at the red line. That's the EBI prediction. Because of that built-in energy limit, the effect just levels off. It saturates. It's a completely different signature. And, once again, they gave us a number. According to their models, the biggest rotation you'd get from this EB effect would be around 15 degrees. A solid, concrete, measurable number. And the result of all of that is this incredible simulation. On the left, you've just got the brightness of the light from the disk of gas, but look at the right. That's the polarization map. You can actually see the twist in those little lines. That rotation is the signature of vacuum birefringence. It's a visible fingerprint of this new physics happening right there at the edge of everything. Now, this isn't just a story about black holes and light twisting through space. Behind all these predictions, there's a really amazing human story about two scientists trying to connect two totally different ways of looking at the universe. You see, this paper is a collaboration between Moses Zhu and Emmanuel Markoulakis. Each of them has developed their own fundamental theory of how the vacuum of space actually works, and this whole black hole project is their way of trying to build a bridge between their two separate worlds. And this table just lays it all out perfectly. On one side, you have Zhu's framework, which sees the universe through the lens of geometry, a structure that can be bent, that can be saturated. But then you have Markoulakis, who sees it as a fluid, a condensate of faster-than-light particles that can flow and evaporate. One guy sees particles as defects in geometry, the other sees them as little whirlpools in a fluid. Their entire massive collaboration really boils down to this one simple but profound question. Can they prove that a number calculated from Zhu's geometry, the refractive index, is mathematically the exact same thing as a number from Markoulakis' fluid, the evaporation density? Because if they can, then they haven't found two new theories. They've found two different languages to describe the same single, deeper reality. So where does all this leave us? Well, it brings us right back from these amazing abstract ideas to something very concrete: observation. All of it. The shrinking shadow, the twisting light, the unification of geometry and fluid, it all comes down to what our best telescopes can actually see. And the final judge in this case is the Event Horizon Telescope. This unbelievable instrument, this network of telescopes that spans the entire globe, is the only thing we have that's powerful enough to maybe, just maybe, see these tiny effects. It's the telescope that gave us those first historic pictures of black holes, and it might just be the key to unlocking a whole new chapter in physics. And this is the punchline. The researchers actually mapped out the exact conditions you'd need for the EHT to spot the difference. And that red star? That marks the parameters they used for their study, and it falls right smack in the middle of the detectable by EHT zone. Their prediction isn't just some sci-fi fantasy. It's something we could actually go out and look for, right now. So the next time the Event Horizon Telescope team releases a new, sharper image of a black hole, we're not just going to be looking at another amazing picture. We're going to be looking for clues. Is it a perfect match for what Einstein predicted a century ago? Or are we going to see a slightly smaller shadow, a subtle twist in the light, the very first hint that we're seeing the universe in a completely new way?